5 times 10 to the power 3 Newton. And the 5 times 10 to the power 3 Newton will generate tensile stress. Okay, because if we were to look back at our free body diagram, AX is moving towards the left, stretching the component. So it's going to be under what? Tension. Okay. So the formula that we're going to use, okay, by referring to the cross-sectional area. So let me write out our E1 is equal to material 1 is equal to 104 times 10 to the power 9 Pascal. And then E2 is equal to 200 times 10 to the power 9 Pascal. Okay. So if we are going to find stress X1, okay, for material number 1, so it's equal to BAX1. So it's under tensile plus by AX over area of 1 plus by E2 over E1 multiplied by A2. Okay. So material E1, okay, is for material 1. So AX is 5 times 10 to the power 3. Material 1, the width is 0.15. Right, you all can see, right, 150. And the thickness throughout is 10 millimeters multiplied by 0.01 plus, okay. So now material 1, okay, so E2 now is equal to 200 times 10 to the power 9 divided by E1, which is 104 times 10 to the power 9. And then area of 2, right? So area of 2, the width is 0.01. And the depth is what? So it's 300 minus by 10 is 0.29. So this will be equal to 200 power 9 divided by 104 power 9 times by 0.01 times by 0.29 plus by 0.15 times by 0.01 equal then 5 power 3 divided by. So it's equal to 706.522 positive times 10 to the power 3 Pascal. Okay, so it is not a very big load. Let me do it again. 200 divided by 104 times by 0.01 times by 29 plus 0.15 times 0.01. 5 power 3 divided by. Hey, I got a different answer now. (706.522). Okay. So this is our axial load, okay, for composite material, for material 1. So you can see it's not that difficult. It's quite straightforward to look for composite material, right? Under axial loading. Okay. So stress X2 is equal to, again, plus by AX because it can be tensile. So now this is equal to E1 over E2 A1 plus by A2. Okay. So I'm just using the formula. So this is 5 times 10 to the power 3. So now E1 is 104 times 10 to the power 9 divided by 200 times 10 to the power 9. And then the area is 0.15 multiplied by 0.01. Okay. And then the whole thing, not the whole thing, then the denominator is plus by the width is 0.01. The depth is 0.29. Okay. So this will be equal to 104 about 200. 10 to the 0.15 10 by 0.01 plus by 0.01 10 by 0.29. Then it's 5 power 3 divided by, so it's equal to 1.35, 1.359 times 10 to the power 6 Pascal. Let me do it again. So 104 divided by 200. 1.359. Yep. Right. So have to take note, the stress x in 1 is power 3. Stress x in 2 under axial load is 10 to the power 6. Okay. So the next thing we're going to do now is we're going to determine stress x. Okay, we're going to determine stress x now due to bending moment. Okay. So we know that the formula stress x for material 1 is equal to N1, okay, mz over izz multiplied by y. And then for material 2 is equal to N2 mz over izz multiplied by y. Okay. So the first thing we have to do, we have to find, or we are going to find the centroid and, okay, and izz, okay, and izz. So we are going to focus on this cross section now. Okay, so hold on. We're going to focus on this cross section now. Okay, so we are going to find the centroid, okay, and izz. So we're going to select material number 1 as the reference material. It's not always have to be material 1. Either one you choose, the answer would be the same. Okay, so N1 is equal to E1 divided by E1. So this is equal to 1. N2 is equal to E2 over E1. So just to recall, E2 is equal to 200 over 104. Okay, so this is equal to 200 over by 104. Okay. So we're going to find the position of the centroid. Okay, so we are going to determine, okay, we are going to determine the position on the centroid. Okay, and we are going to determine from the top. So we are going to determine what is our y bar. Okay, for now we don't know. Okay, so for composite material is not so, it's more complicated to find centroid, but not impossible. But always remember the what? The height or the height or the depth or the depth is held constant. Okay. So now we are going to determine the centroid. Okay, centroid. Okay. So find sandwich material. Centroid. Okay. So same thing like what I've talked to you guys. So we can create a table section. Okay, so section 1 and then section 2. But this table need to have more information because it is a sandwich material. Okay, so the next one we are going to put N or materials. So we know that this has material number 1. This has material number 2. Okay, so this is our section 1, section 2. Okay, and then I like to go by width and depth. Or before we go there, we have to put in our N value. We know that this is 1. This is 200 over 104. Okay, that's what we know. And then from here, right? So the axis of interest is the green. So this is our width. And this over here will be our depth. Okay. So we have N multiplied width or N width. Remember the width is changing. And then multiply by depth. Okay. So material 1 is 1 times by the width is equal to 150. The depth is 10. Okay. Material number 2, the width is 10. So you have to include 200 over 104 multiply by 10. And the depth now is 290. Okay. So we compute this out. So it's 1500. So 200 over 104 times 10 times by 290. So this is equal to 72500 over 13. Okay. And then next we're going to find the individual section Y bar. Okay. We'll find the individual section Y bar. So Y bar, and as you can see down here, the data is from the top. So the thickness did not change, right? So 10 divided by 2. This is 5. And this is 10 plus by 290 divided by 2. Okay, so 10 plus by 290 divided by 2 is 155. And then the last column, we are going to calculate our N, W, D multiplied by Y bar. So 1500 times 5 is 7500. 72500 over 13 times 155, it is 864.423 times 10 to power 3. Okay, then you do a summation. You add 1500 plus by 72500 over 13. You get 92123 over 13, and then this one will be equal to 10500 plus by 864.423 power 3. You got 871.923. So from here, our global centroid for the entire structure is equal to 871.923 times 10 to the power 3 divided by 92,000 over 30. So it's equal to 123 0.207 millimeters from the top. Okay, from the top.